Good morning, grade 11. Hope you are all doing well and being safe. This is Miss Pamela giving the physics course. Today we are going to continue section 1 in chapter 7, which talks about planetary motion and gravitation. So please open up your books on page 182 and follow up with me. First, we are going to talk about Newton's law of universal gravitation. Isaac Newton compared the acceleration of the moon to the acceleration of objects on Earth, believing that gravitational forces were responsible for each. So he believed that gravitational forces were responsible for acceleration of objects on Earth and for the acceleration of the moon. Newton was able to draw an important conclusion about the dependence of gravity upon distance. So he concluded a very important thing about how gravity depends on distance. This comparison led him to conclude that the force of gravitational attraction between the Earth and other objects is inversely proportional to the distance separating the Earth's center from the object's center. So as the distance between Earth's center and between an object's center increases, the gravitational attraction between them decreases. This is what we mean by inversely proportional. And when this distance decreases, the gravitational attraction increases. But distance is not the only variable affecting the magnitude of a gravitational force. Consider Newton's famous equation, which is Newton's second law. The net force acting on an object is equal to the mass of the object times its acceleration. Newton knew that the force that caused the apple's acceleration, which is gravity, must be dependent upon the mass of the apple. And since the force acting to cause the apple's downward acceleration also causes the Earth's upward acceleration, which is Newton's third law, action-reaction forces, that force must also depend upon the mass of the Earth. So, not only the distance affects gravitational attraction, also the mass of objects affects gravitational attraction. So for Newton, the force of gravity acting between the Earth and any other object is directly proportional to the mass of the Earth, directly proportional to the mass of the object. So as the mass of Earth or mass of the object increases, this gravitational force increases as well. And this force is inversely proportional to the square of the distance that separates the centers of the Earth and the object. So as the square of the distance increases, the gravitational force decreases. But Newton's law of universal gravitation extends gravity beyond Earth, so it doesn't only talk about Earth and objects on Earth. Newton's law of universal gravitation is about the universality of gravity, so it talks about the whole universe. All objects attract each other with a force of gravitational attraction. Gravity is universal. This force of gravitational attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance that separates their centers. So this universal gravitation extends beyond Earth. It doesn't only talk about the gravitational attraction between Earth and an object on Earth or near Earth. It talks about all objects in the universe. So all objects in the universe have gravitational attraction between them, which is directly proportional to the masses of the objects and inversely proportional to the square of the distance that separates the object's centers. Newton's conclusion about the magnitude of gravitational forces is summarized symbolically as the equation you see in front of you. So this equation summarizes Newton's law of universal gravitation. So as you can see, we have two masses, m1 and m2. There's a force of attraction, which is gravitational attraction, from m2 on m1, which is F1. And there's a force of attraction from m1 on m2, which is F2. And the distance that separates them is equal to r. So the magnitude of F1 is equal to the magnitude of F2, which is equal to g times m1 times m2 over r squared, where F1 is the gravitational force acting by mass 2 on mass 1, measured in newtons. F2 is the gravitational force acting by mass 1 on mass 2, also measured in newtons. G is the gravitational constant, which you must memorize, equal to 6.67 times 10 to the power negative 11 Newton.meter squared per kilogram squared. M1 is the mass of object 1 measured in kilograms, and M2 is the mass of object 2 measured in kilograms. R is the distance between the two objects measured in meters. Since the gravitational force is directly proportional to the mass of both interacting objects, more massive objects will attract each other with a greater gravitational force. Of course, if the mass of the object increases, if the mass of one object or both objects increases, the gravitational force acting between them increases as well. So as the mass of either object increases, the force of gravitational attraction between them also increases. If the mass of one object is doubled, then the force of gravity between them is also doubled. If the mass of one object is tripled, then the force of gravity between them is also tripled. If the mass of both of the objects is doubled, then the force of gravity between them is quadrupled, which is times 4, and so on. Since gravitational force is inversely proportional to the square of the separation distance between the two interacting objects, more separation distance will result in a weaker gravitational force. So as two objects are separated from each other, the force of gravitational attraction between them also decreases. If the separation distance between two objects, for example, is doubled, increased by a factor of 2, then the force of gravitational attraction is decreased by a factor of 4 because it is squared. If the separation distance between any two objects is tripled, increased by a factor of 3, then the force of gravitational attraction is decreased by a factor of 9, which is 3 to the power 2. By rearrangement of Newton's law of universal gravitation equation, we can find the mass of one of two objects if we know the gravitational force between them and the mass of the other and the distance between them using the equation you see in front of you. M is equal to F times r squared over g times m2. And we can also know the distance, the separation distance between two objects if we know their masses and the gravitational force between them using the other equation you see in front of you. R is equal to radical g times m1 times m2 over f. Now we are going to talk about the period of a planet orbiting the Sun. By combining Newton's law of universal gravitation, Newton's second law of motion, which is F is equal to m times a, and the equation to find centripetal acceleration, as you can see on page 183, we can conclude an equation that allows us to calculate the period of any planet orbiting the Sun. You can see the equation in front of you. T, which is the period of the planet, which is the time it takes the planet to complete one revolution around the Sun measured in seconds, is equal to 2 pi radical r cubed, where r is the average distance from the Sun measured in meters, over the gravitational constant, which is equal to 6.67 times 10 to the power negative 11 Newton dot meter squared per kilogram squared, times the mass of the Sun, which you also need to memorize as being 1.99 times 10 to the power 30 kilograms. By rearranging this equation, we can find the distance of any planet from the Sun if we know its period, using the equation you see in front of you. Cubed radical t squared times g times ms over 4 pi squared, where r is measured in meters, the period is in seconds, g is the gravitational constant, ms is the mass of the Sun, and over 4 pi squared. In front of you, you can see an example of Newton's law of universal gravitation. This is the gravitational force between the Sun and Earth. F is equal to g times m1 times m2 over r squared. G is equal to 6.67 times 10 to the power negative 11. M1 is the mass of the Sun, 1.99 times 10 to the power 30 kilograms. M2 is the mass of Earth, which is equal to 5.98 times 10 to the power 24 kilograms. And R is the distance between the centers of the Sun and the center of Earth, which is equal to 1.5 times 10 to the power 11. The answer is 3.52 times 10 to the power 22 newtons. This is the gravitational force between the Sun and Earth. As a homework, please solve numbers 8 and 9, page 185, and the following two numbers. Number 1. The gravitational force between ball 1 and ball 2 is equal to 120 newtons. What is the mass of ball 2 if the mass of ball 1 is 2 kilograms and the distance between them is 160 centimeters? Number 2. How far is Mars from the Sun if it takes 686.971 Earth days to orbit the Sun? Your homeworks must be done and submitted to me on Tuesday, 19 May. Thank you, good luck, and stay safe.